Good day. I am Dean Robin De Leon along with my partner Melvin Dayao, presenting our thesis titled Development of Bambusa blumeana Fiber Reinforced Concrete with Enhanced Structural Performance through Alkali-Silane Treatment. Our advisor for this study is Dr. Jeremiah C. Meliare. For the background of the study, the construction industry has increasingly recognized the need for sustainable materials that reduce environmental impact while maintaining or enhancing structural performance. In this context, natural fibers have gained significant attention as potential reinforcements in concrete, offering a more sustainable alternative to the traditional synthetic fibers. Bamboo fibers stand out due to their high strength-to-weight ratio, renewability, and abundant availability, particularly in tropical regions. However, the use of bamboo fibers as a reinforcement material in concrete is strictly in the early stages of development. Raw bamboo fibers are susceptible to moisture absorption, biological degradation, and variability in mechanical properties, limiting their application in concrete composites. Chemical treatments such as alkali and silane treatments have been proposed to improve the compatibility of bamboo fibers with cementitious materials, enhancing their durability and mechanical properties to address these challenges. For the hybrid treatment of alkali and silane, Valadez Gonzalez studied the enhancement of the interfacial shear strength between the Heineken fibers and thermoplastic matrix through the combined treatment. Their fibers were treated with 2% sodium hydroxide solution to remove surface impurities, followed by saline application using 1% silane and 0.5% dichromyl peroxide mixture in methanol water. Their treatment altered the fiber morphology and composition with FTIR and X-ray photoelectron spectroscopy, confirming effective silane deposition, and as a result, the composite's tensile strength improved from 31 to 27 megapascals. The objectives of this study is to investigate the effectiveness of an alkali-silane treatment on the chemical composition, thermal stability, surface morphology, and thermal behavior of bamboo fibers. This will be determined through the changes in the chemical composition of the fiber surface through FTIR spectroscopy, the thermal properties of the fiber through TGA, and the morphology of the fiber through SEM. Then we should determine the optimal combination of the alkali and silane concentrations that maximizes the improvement in the fiber properties. The second objective is to assess the effectiveness of the treated bamboo fibers as a reinforcing material in concrete, which can be determined through the mechanical properties of the composites such as the splitting tensile strength test to ASTM C496, the flexural strength test to ASTM C78, and the compressive strength test through ASTM C39.
In our study, we replicated the experimental procedure used by Asomani et al. In their research on alkali-silane chemical treatment. Our study followed a similar methodology but focused on a different type of fiber and composite material. Specifically, we used bamboo fibers. They study sourced the needed Bambusa blumeana samples from Nevaisia. Before the bamboo samples undergo chemical treatment, they had to undergo a pretreatment process where the bamboo internodes were dried at an outdoor surrounding temperature of about 36 degrees Celsius over 7 days period. Afterwards, the bamboo steers were cut to approximately 6 by 5 by 1 mm and then washed with deionized water to remove any impurities. For the alkali-silane treatment, the first steps involved performing an alkali treatment. In this study, sodium hydroxide was used. Bamboo samples were exposed to 5% sodium hydroxide for 48 hours at 25 degrees Celsius as proposed by the study of Kaima et al. Following the alkali-silane treatment was conducted using the silane coupling agent 3-metacryloxypropyl trimethoxysilane or KH570. Three different concentrations of KH570 were tested: 2%, 5%, and 10% by weight as recommended by Wang et al. The alkali-treated fibers were soaked at 28 degrees Celsius for 4 hours. After soaking, the sample were washed with distilled water and then dried in an oven at 80 degrees Celsius for 12 hours. To assess the impact of alkali-silane treatment of the bamboo fibers, various tests were conducted. These tests examine the fiber's chemical composition, thermal stability, surface morphology, and thermal behavior. First is Fourier transfer infrared spectroscopy. It was used to compare the chemical composition of untreated and treated fibers, revealing changes in their functional groups. Next is thermogravimetric analysis that determined the fiber's thermal stability by analyzing weight loss patterns at different temperatures, providing insight to how the treatment affects the thermal decomposition. And last is scanning electron microscopy that was used to examine the surface morphology of the fiber, which allowed for the observation of changes in surface roughness and the presence of any chemical deposits left by the treatment. After conducting the chemical analysis of the treated fibers, the author selected the concentration that most effectively enhanced the characteristic of the fibers. After that, the methodology of the treatment of selected concentration was repeated on a larger volume of samples, which were then used as reinforcement materials in concrete mix. For the concrete preparation, to prepare the concrete composite for mechanical testing, ASTM standard were followed, and 20 grade cement was used mixed with sand and aggregate in a ratio of 1 to 1.5 to 3 by mass with water cement ratio of 0.5. All samples underwent a standard curing procedure for 7 days before the mechanical testing. For the mechanical testing, the authors will use three testing standards for the mechanical properties. The standard test method for splitting tensile strength, flexural strength, and compressive strength using the universal testing machine of Mapua University. For the splitting tensile strength test, cylindrical molds with a diameter of 6 inches and height 12 inches were used. Three types of concrete or samples were prepared. Non-reinforced concrete. Next is non-treated bamboo reinforced concrete and treated bamboo reinforced concrete for flexural strength test. Rectangular molds measuring 6 inches by 6 inches by 21 inches were used. Three types of concrete samples were prepared. The non-reinforced concrete, non-treated bamboo fiber reinforced concrete, and treated bamboo reinforced concrete. And lastly, for the compressive strength test, cylindrical molds with a diameter of 6 inches and height of 12 inches were used.
For the chemical treatment, significant mass was also observed according to the results. Moving to the results of the Fourier transform infrared spectroscopy analysis. The 3345 per centimeter OH peak indicative of hydrogen bonding shows a significant reduction, especially in the sample treated with 5% NaOH and 10% KH570, implying a disruption in hydrogen bonds and a decrease in moisture content. The 1029 per centimeter peak associated with lignin also decreases across all treated samples, suggesting partial removal of lignin. Similarly, the 2904 per centimeter CH stretching peak shows a reduction with the most significant reduction in the 5% NaOH with 10% KH570 of hemicellulose and cellulose. The disappearance of peaks at 1511 and 1424 per centimeter represent the aromatic skeletal vibrations in lignin, indicating effective lignin removal. This result explains that despite the hydrophilic nature of bamboo fibers, alkali-silane treatment can significantly reduce their moisture retention. The treatment removes hemicellulose and lignin, which are hydrophilic components of the fiber. By removing these, the treatment exposes more cellulose hydroxyl groups, making the fiber surface more reactive, so that when silane reacts with the exposed hydroxyl groups, it introduces hydrophobic groups onto the fiber surface, while reducing the hydrophilic sites that water can bind to. The appearance of a 1503 per centimeter peak, especially in the 5% NaOH and 10% KH570 treated sample, indicates SiC bonding, suggesting effective bonding between the silane coupling agent and the bamboo fiber surface. These findings suggest that higher silane concentrations intensify fiber modification, resulting in a more structurally stable and compatible reinforcement for composite applications. This figure presents the thermodynamic analysis curves of the tested samples, illustrating the relationship between temperature and weight loss percentage. In the higher temperature range, about 250 to 390 degrees Celsius, there was significant weight loss for all samples, with the untreated sample showing the highest weight loss at 64.30 percentage by weight, followed by the fibers treated with 2% KH570, 5% KH570, and 10% KH570, which exhibited the lowest weight loss at 59.99 weight percent. This pattern suggests that fibers treated with 5% NaOH and 10% KH570 enhanced thermal stability among the samples as it retained more mass during thermal degradation. The TGA and DTG results indicate that fiber that is treated with 5% NaOH with 10% KH570 is the most thermally stable among the tested samples, as it consistently exhibited lower weight loss percentage throughout the analysis. The minor peaks observed in the DTG curves of all samples, especially the absence of a small curve at 308.5558 degrees Celsius of the treated samples, further support the notion that thermal treatment has improved the overall thermal stability of the fibers. Additionally, the results imply that thermal degradation is influenced by the structural changes induced by the treatments, leading to variations in thermal stability among the samples. Moving on to the results of the scanning electron microscopy. In Figure A, the untreated bamboo fibers have a rough and sharp structure compared to the smooth surface of the treated fibers in Figure B, C, and D. Moreover, the surface of the treated fibers became progressively smoother as the concentration of the KH570 increased, and furthermore, impurities are present throughout the samples, but more are eliminated as the KH570 concentration increased, which can be observed in the bumps on the cellulose microfibrils and the lumen structures. The cellulose microfibrils are the elongated parallel lines, while the lumen structures are short rounded rectangles. Additionally, the empty lumen structures are visible in Figure A, which decreased in appearance as the concentration of KH570 increased. This reduction may be attributed to the filling of the empty lumen structures with acetylene. The smoother surface, removal of impurities, and the disappearance of empty lumen structures all suggest successful bonding of the fiber sample with acetylene. The combination with fibers treated with 5% NaOH and 10% KH570 appeared to be the most effective for this chemical analysis. And based on the results of the FTIR thermal stability and analysis and surface morphology analysis, the optimal treatment concentration for enhancing the properties of bamboo fibers and making them ideal for use as a reinforcement material in concrete was determined to be 5% NaOH combined with 10% KH570. This treatment concentration provides a balance between fiber modification and structural enhancement, making it the most suitable for enhancing the properties of bamboo fibers and their potential as a sustainable reinforcement material in concrete.
And for the mechanical properties of concrete composite, the maximum load and sample dimensions were used to calculate the corresponding tensile, flexural, and compressive strength. For the splitting tensile strength test, the table presents the test results, including maximum force, maximum stress, and calculated tensile strength. Treated bamboo fiber reinforced concrete exhibited the highest performance with a maximum force of 157.6 kilonewton and a maximum stress of 8.64 megapascals and a calculated tensile strength of 2.16 megapascals. This represents an 11.1% increase over the untreated fiber reinforced concrete, which had a tensile strength of 1.95 megapascals and a 24.9% increase compared to non-reinforced concrete with a tensile strength of 1.72 megapascals. For the flexural strength, treated bamboo fiber reinforced concrete exhibited the highest performance with a maximum force of 14.98 kilonewton, a maximum stress of 3.56 megapascals, and a calculated flexural strength of 2.58 megapascals. This represents an increase in flexural strength compared to the untreated fiber reinforced concrete and non-reinforced concrete, which had a flexural strength of 2.46 megapascals and 2.06 megapascals respectively. And for the compressive stress, treated bamboo fiber reinforced concrete exhibited the highest performance with a maximum force of 235.3 kilonewton, a maximum stress of 12.89 megapascals, and a calculated compressive strength of 12.89 megapascals. Compared to untreated fiber reinforced concrete, the treated fiber reinforced concrete showed a slightly 0.9% increase in compressive strength, with a compressive strength of 12.78 megapascals. It also demonstrated a significant 26.2% increase in compared to non-reinforced concrete, which had a compressive strength of 10.21 megapascals.
To conclude the study, the authors investigated the effects of the alkali-silane treatment of bamboo fibers, and upon interpretation of the results from the virus test, the authors obtained the following findings. The alkali-silane treatment effectively improved the Bambusa blumeana fibers by removing impurities, creating a bridge between hydrophilic fibers and hydrophobic materials, enhancing surface morphology, increasing thermal stability, and reducing moisture retention. The FTIR spectra showed changes in peak intensities and positions indicating impurity removal, including moisture, lignin, and hemicellulose. The spectra also revealed the removal of OH bonds and the formation of silicon O-C bonds and silicon C bonds, confirming KH570 bonding to bamboo fibers. TGA curves show that the treated fibers retained more mass when heated. Untreated fibers had two significant mass loss spikes at 308.56 degrees and 356.50 degrees Celsius, whereas treated fibers exhibited peaks at higher temperatures at around 356.75 degrees Celsius, indicating greater thermal stability. SEM micrographs revealed smoother fiber surfaces, impurity removal, and filled lumen structures, suggesting KH570 adhesion. And the treatment with 5% NaOH and 10% KH570 yielded the best results with maximum impurity removal, strongest KH570 bonding, superior thermal stability, and the smoothest fiber surface compared to untreated or lower KH570 treatments. The treated bamboo fibers serve as an effective reinforcing material in concrete composites, enhancing key mechanical properties such as the splitting tensile strength, flexural strength, and compressive strength. The treated reinforced composites showed superior performance compared to untreated and non-reinforced composites. According to the results of ASTM C496, the splitting tensile strength increased from 1.73 megapascals to 1.96 and 2.60 megapascals. ASTM C78 revealed that the flexural strength increased from 2.06 to 2.46 and 2.58 megapascals. And the ASTM C39 results revealed that the compressive strength increased from 10.22 to 12.79 and 12.9 megapascals, with the treated bamboo fibers exhibiting the highest strength.
And that is all for our presentation.